Thank you, Rob sir, for giving me an opportunity to be a part of this webinar. Uh, Indeed, it was a great pleasure that you have invited me for this webinar in your college, in your esteemed institution. And as your principal, sir, and your IPSC coordinator, ma'am, told, the applications of mathematics and applications of number theory and algebra in particular in computer science, the topic I chose because you told that you wanted a topic which is easily understood by the students of degree batch, undergraduate students. And of course, as I can see, there are a few participants who are a bit of higher level, but of course, I hope that they will also be enjoying my talk. Thank you. So with that note, let me begin. I would like to share the screen, and please tell me, sir, if it is visible to you. Okay, so without much delay, we can start the session straight away. Can you see it, sir? Rob, sir?
Okay, miss. It's visible.
Okay.
Okay.
Yeah, okay.
Okay.
Yeah, thank you. So in between, if you have any doubt or any glitches in between, whether my video is not visible to you or the screens are not visible, please inform me. The scheme of talk is planned in such a way that we will discuss the concept of number theory, because I think the students of UG may be only fifth semester students, and they'll be dealing with number theory only in the coming semester. And so I have given a small introduction to what is a number theory and what are the preliminaries that we would like to have before going on to the further slides. And then, of course, the applications of number theory and applications of linear algebra. So that is the scheme of talk that we have planned here. So number theory is a theory which is mainly focusing on numbers. So in earlier days when we were students, maybe you can ask the students can ask their parents or elderly people who are above the age of 40 years. We had in school the first mathematics that we used to learn was arithmetic. Nowadays, I think it is not, that term is not used anywhere. Because even in the first standard or second standard. Okay, so previously we used the term arithmetic to denote the concept of numbers. That means the basics of mathematics, we used to call it as arithmetic. And that theory developed to the present form of number theory in the early 20th century only. And mathematics, of course, as all of you know, is the foundation of many of the science and engineering disciplines, where, of course, number theory forms the foundation of mathematics. So that is the importance of number theory that I wanted this younger generation to understand. And number theory primarily deals with the nature of integers. And we know what are integers. Integers are the positive integers are, of course, the natural numbers. The negative integers are the negatives of all the natural numbers, and 0 is also, of course, an integer. So the number theory primarily deals with the nature of integers, the properties of integers, and so on. And the questions in number theory are concise, and they are mainly based on solution of the unique factorization theorem. And what is the unique factorization theorem? We'll be dealing in the next slides in the preliminary section. And later on, the process of reconstructing the unique factorization theorem, some new concepts such as the complex integers, ideal numbers, ideals, etc. were introduced, which form also a part of algebra that you will learn. You have been learning in this semester also, rings, subrings, and so on. So ideals, ideal numbers, and complex integers are all also the new what do you mean? The new concepts which were evolved as the result of the research of number theory, and still researches are going on in this fields. Now, what are complex integers means? It is a complex number of the form a plus ib, where a and b both should be integers. And what are ideal numbers means? Ideal numbers are preferably formed using the factors of unity. And these things you will be learning in the complex analysis and algebra, of course. And ideal numbers were introduced by Kamma, and ideals were introduced by Dedicant by studying the concept of ideal numbers by Kamma. And the results from number theory have many numerous applications, practical applications including security, memory management, authentication, coding theory, and so on. And we have taken this topic especially for this webinar because we mathematicians do prefer to learn pure mathematics rather than knowing what is being done using our theory in real life. But when I was a student, I usually had a thought why we are learning these modulo, why we are learning these factorization theorems, why we are learning these things. But when it came to engineering applications and so on, those people are doing their work purely based on our theory that we were discussing in our classrooms. But we are unknown that our theory has so many applications in those areas where people use them for making our own life simpler. So that is the main reason why we have taken such a topic, just for making you slightly aware of the things that you are learning in your subject, how they are being used in the real world applications and so on. Okay. Now, the preliminary part is that number theory usually deals with the first concept of number theory. The first topic that we will be discussing in number theory is divisibility. And what is divisibility? Of course, we can see that if an integer a can be expressed as a product of two integers, then those two integers are said to be set to divide these integers. For example, if you take 6 is equal to 3 into 2, we can say that 2 divides 6, and we can say 9 divides 18 because 18 can be expressed as a multiple of 9, and so on. So that is the concept of divisibility. And a unique factorization theorem that we had discussed in the previous slide, it says that every number, every integer can be expressed as the product of primes or product of powers of primes. So for example, if you take 100, you can divide 100 by 2, you will be getting 50. 50 again you divide by 2. So 100 can be expressed as 2 raised to something into 5 raised to something, and so on. So that you can compute. And so that is the terminology, or that is the meaning of the unique factorization theorem. And every integer can be uniquely factored based on the primes or powers of prime. That is what is unique factorization theorem saying. And division algorithm is another important theorem that we will learn in number theory. And that is given by you are studying in algebra also. If a is an integer, b is another integer, there are definitely two unique integers q and r such that a is equal to bq plus r, where q is called the quotient and r, of course, the remainder. Now, the main important concept of a number theory is modular arithmetic. Given an integer n greater than 1 called the modulus, two integers are said to be congruent modulo n if n is a divisor of their difference. That means we will write a is congruent to b mod n if we have a minus b as a multiple of n. So for example, you can take 12 is congruent to 1 mod 11. Simple example. Or 5 is congruent to 5 is congruent to 3 modulo 2, because 5 minus 3 is definitely a multiple of 2, and so on. So that is what is the modular arithmetic. And then the Euclidean algorithm, of course, the Euclidean algorithm is an algorithm used for finding the greatest common divisor of two numbers, a and b. Suppose you are having two numbers, say 110, which is the greatest common divisor? Of course, it is 10. And so by Euclidean algorithm, you will be getting the greatest common divisor of 110, or any large number you take. Okay, so actually these concepts are being used in computer science to reduce the complexity. We will be discussing the examples of that. Now coming to the applications of number theory, the main applications, the most simplest I have dealt with. So the most simple applications of number theory that we can discuss here is hash function, pseudo-random numbers, then fast arithmetic operations, linear congruences, and of course cryptography. Now we'll be discussing with each one of them in detail. What are hash functions? So hash function means, suppose we are having a very big database. We are having a very large collection of objects, and out of which we should pick out one object at random. How we will be able to do that? So if it is known as the sorting of an array in computer science language. So if the array is sorted, we can use a binary search approach, or there are many approaches, different approaches we can use, and they have a runtime complexity. Now, what do you mean by runtime complexity is that if you have an algorithm, there can be some algorithms which gives you the output in a polynomial time, and there are some algorithms which gives you the output in a non-polynomial time, and there are many applications. There are many types of runtime complexities available in computer literature, and we can see that the polynomial time algorithms are the most user-friendly algorithms, because see, again, somebody is making some scratches on the slides, I hope. Rosa? Hello? Okay. Okay, thank you. It's gone. Okay, thank you, sir. With the, I lost my connection, sorry. The continuity is gone if you make such disturbances. So please don't disturb in between. Okay, so if by using such binary search algorithms and all, we have a runtime complexity of order of log n, which can be further reduced by the use of simple hash functions, mainly using number theoretical concepts, and we can have it as a constant runtime, say order of 1 and so on. And so such functions are called hash functions, and we will see the example of a hash function here. For Zm is equal to 0, 1, 2, etc. up to m minus 1. Zm, we all know, those who have learned algebra may be knowing what is the notation Zm means. And so we define a hash function h from the set of all integers to Zm as h of k is congruent to k mod m. So that means h maps all the integers to a subset of size m by computing the remainder of k by m. And hashing is the transformation of a string of characters of fixed length to some keys. So first thing is that we will convert the string of characters into some keys, and then the keys will be assigned a particular integer modulo value. And then using those integer modulo value, we can retrack what this original object was. That is the technique behind hashing. So hashing is used to index and retrieve items in the database because it is faster to find them. So we can see one more example. And when we assign a hash function, we have to keep in mind that it always returns a number for a particular object, because as I discussed in the previous slide, every object will be converted to every object has a fixed length, or a string of fixed length will be converted to a key or a particular number, and that particular number will be assigned an integer based on the modulo value. And such on assigning such values, it always returns a number for an object, and two equal objects will always have the same number, but two unequal objects not always have different numbers, because we can see in the next example. Suppose we have a data in which you have 4 objects, and these 4 objects are given the hash codes, namely 4, 16, 68 and 125, and based on the previous hash function that we had discussed in this slide, we had discussed what is a hash function. This function we had discussed, a hash function. H is a function from Z to Zm such that h of k is congruent to k mod m. So here in this example, they have taken modulo 5 values. So as I told you in the previous slide, what is congruent modulo 5? 4 is not divisible by 5. So 4 when divided by 5 will give you the remainder 4 itself. So you will assign 4 to 4. 16 when divided by 5 will give you the remainder 1. And so 16 modulo 1 means 16 is congruent to 1 modulo 5. And so 16 is assigned the value 1. 68 is congruent to 3 modulo 5 because 68 minus 3 is a multiple of 5. And so 68 we will assign the value 3. And 125 because it is a multiple of 5 we will assign the value 0 itself. But the main drawback of this method is that the table indices that we are giving based on the hash function is 0 is assigned for object 4, 1 is assigned to object 2, 3 is assigned to object 3, and 4 is assigned to object 1. But whenever we assign the value 0, 0 is automatically assigned to object 4. So if in the database we have another object which is having a multiple of 5 as the hash code, again 0 will assign that object also. Okay, that is what we have discussed in the previous slide. Two unequal objects need not always have different numbers. So that is the main drawback of assigning hash functions, and this is known as the collision, because we can have objects put into a hash table. It is possible that different objects might have the same hash code, and this is called what is collision. But there are, in modern computer science, there are many more approaches which are dealing with collisions also, how to solve these collisions. They are doing several approaches, but that is also one full session for a webinar, and so I'm not going to the details of it. And so as a summary, what is a hash function? Is a function which when given a key generates an address in the table. And an example of hash function in real life can be the books arranged in a library. We have a call number for each book, and so when we give that call number to the system will give the full details of that book. So that is what is called a hashing. So just allocating a particular key or particular code to an object. So that is like an address. Okay, that is the best example of hash function that we can see in the real life. Now the next concept is pseudo-random numbers. Now pseudo-random numbers are numbers that are generated from weak random sources. And what are random numbers? Random numbers are numbers which are generated randomly. So pseudo-random numbers are those numbers which does not exist in real, but we generate it in a random fashion. That is what is called pseudo-random. It is not random numbers as we have dealt in the case of probability and all, but it is a random picking in the computer science language, and that is why they call it pseudo-random numbers. And one method of generating pseudo-random numbers is a linear congruential method. And an early computer-based pseudo-random number generator, that is what is the short form of pseudo-random number generator, is given PRNG, and it was suggested by John von Neumann. I'm sorry that I have forgotten to put a V capital here. It is John von Neumann, and it was in the early 90s, that is 1946, that we can say, early for us of course, and it is known as the middle square method. And what is the method? If you have a number, you square that number, you take it as if you have a 4-digit number, you will square it, and if you are getting it as a 7-digit number, you will make it an 8-digit number by adding a 0 on the left side. Then you will pick out the middle 4 numbers, and that gives you a random number. And you repeat the same procedure. So I'll give you an example. If you have the number 1111, you square that number 1111. If you have a calculator, you can do it. You will get 1234321 as the number. But if you count the number of digits, you can see that there are only 7 digits. But originally it was a 4-digit number. So squaring the 4-digit number, we expected it to be an 8-digit number. Okay, I don't know whether all the 4-digit numbers will, of course, they will not give you, but the square of a 4-digit number, we are assuming it to be an 8-digit number, and we are putting it as 0 there so that we can delete the first 2 digits and the last 2 digits to obtain a 4-digit number again. Otherwise, we will not be able to do that in a pattern here. That is why we are adding a 0 towards the left. And we again get an 8-digit number. You delete 0, 1 and 2, 1 on this side. You will be getting the number 2343. Now 2343 is a random number. Now again you take the square of 2343, 2343. So you will be getting some other number, of which the middle 4 numbers will be 4896. So this is the method of assigning some PIN or a personal identification number like thing for people. So that is the method of dealing with pseudo-random numbers. And the main problem that this type of squaring the number gave is that the numbers started repeating after a few iterations. And so the people wanted to make more sort of random number sequences and so on. And what technology they used is they use the linear congruential method, and where they will produce a sequence of integers, say x1, x2, etc., between 0 and m minus 1, of course, because where they are taking congruent modulo m. And what they will take is, they will take a recursive relationship, xi plus 1 is equal to a xi plus c mod m, where a is the multiplier of our choice. We can decide what our a should be. Sorry, C is the increment. Increment means how much shift or how much we have to increment. That is also our choice, and M is the modulus value. So depending upon these choices A and C, we can create a numerous number of random sequences. So that is the main advantage of linear congruential method for choosing random pseudo-random numbers. Okay, and using of course the help of algorithms, this can be done within polynomial time. Now coming to the next application of number theory is what is the Caesar's encryption process. Now the name Caesar's encryption process is because it was first formed by Julius Caesar, of course. And what he did is he wanted to give some message to his friend. I exactly don't remember the story behind that. Caesar wanted to give a message to somebody without the knowledge of others, and so he wanted to encrypt his message. He wanted to code his message. So what technique he used is he replaced each letter by the third consecutive letter. So for example, if we wanted to start a message using the letter A, what he did is he will replace A by the A plus third letter. That means he will replace A by 3. Okay, likewise, he replaced each letter in that sentence, and he made a encryption technique, and that is replaced by the our function, which is modulo function, of course, because there are only 26 alphabets in English. We have f of p is congruent to p plus 3 modulo 6. Why we are taking modulo? Because we have, if we have a long sentence, say 100 words in a sentence, we have to repeat A to Z only, and so we have to come back again to the, we have to fix our limitations to this A to Z values, and that is why we are taking modulo 26 there. So for example, M is assigned the value 12. M is the 12th position. You have to count A to M. So f of 12 is congruent to 12 plus 3 mod 26, and that is equal to 15. And what is 15 corresponding to? 15 is corresponding to the letter P. So me too in the park is replaced by this. So whenever somebody else sees this, they will never understand what is given, what is the message that they have given. So if this person, if the person who knows this type of encryption process, that if there are friends A and B, and will be having a common encryption pattern, they will say that whatever I want to say, I will shift it to 3 places. Okay, so this is the this is what he has told B. So whenever B gets this message, what B will do? He will shift backwards from 3 positions. So if he get the first letter as P, he will identify that it is not the letter P, but it is the third letter back to P, and that is why he gets it as the message. So that is given by the mathematical notation. F inverse of P is congruent to P minus 3 mod 26. Now, but this technique is much more simpler because we are shifting only 3 places apart. Okay, so Caesar cipher can be generalized as a shift cipher, where we can, okay, this is what we have discussed in the previous slide, P plus 3 we will take. So a much more better way of encrypting is f of P can be made congruent to AP plus B mod 26. So only if people know what is A and B, they will be able to decrypt it easily. Okay, otherwise the decryption process will not be that easy. Okay, unless we know what is A and B, the decryption process will not be that easy. And so that process is what is called affine transformation. And we have, say for example, K is the corresponding to the integer 10. And so if f of 10 is equal to or is congruent to 7 into 10 plus 3 mod 26, then this value will be is equal to 73 mod 26. And what is 73 mod 26? It is 21. 21 corresponding to the letter V. So from K to V, how K has reached V, if a person does not know this type of decryption or encryption method, it is very difficult to find out what is V in terms of what is V, or what is, from where did we get V from K, and so on. Okay. And another thing is that, so cryptography routinely needs to find the GCD of pairs of numerous numbers, say 10 raised to 100 or 10 raised to 1000 and so on. But the Euclidean algorithm has very well reduced the complexity to say about 100 or 1000 steps. And that is also the application of number theory in cryptography. Okay. So this much are the applications of number theory in computer science. And I hope so far it is okay for all of you. Should I break for a few seconds, or I should go for the applications of linear algebra straight away? Rofsa?
Okay, Miss, you can proceed. Okay.
It's okay for you, no? Or should I pause for a second? If anybody is having any doubts in number theory, they can ask, or shall I continue?
Questions may be in the last, I think.
Okay, fine. Thank you. Okay, so applications of linear algebra. Now, linear algebra is a branch of mathematics which we know as a branch which deals with vectors, with matrices, and with transformations, and so on. And we ideally understand linear algebra as a very higher level of mathematics. But remember that whenever computer science came into existence, in computer science without linear algebra, nothing can be made. Because we are saving and we are seeing whatever in computer in terms of matrices and matrices only. So whenever you look at a picture, you have to understand that behind the picture there is a matrix. Whenever you see we are doing some games, or whenever we are playing with images, we have to understand that some sort of linear algebra is running behind all these things. So mainly linear algebra is used in computer animation, computer graphics, namely image representation, storage, computation, and so on, and in numerous other applications, of which only a few I have taken in this section. And the simplest sense, the computer graphics are images viewed on a computer screen, and the images are generated using computers and manipulated by computers. But underlying these images, what happens is we have the mathematics of linear algebra. So if you see the picture, it is the picture of a sparrow or a picture of a kingfisher, whatever bird, name of the bird you can call it. I am very poor in naming the birds. I don't understand what bird it is, but it is a very beautiful picture. But behind this picture, there are so many pixels, and behind this picture, there is a matrix which we cannot view as such. Okay. For example, if you want to have the image H of the letter H, what we require some data matrix, say of this form. 0, 0, 0, 1, 1, 1, 0, 1, 2, 0, 1, 2, and so on. These things we are not so familiar with how these people are getting this matrix. They may be encoding in some pattern. They have got a matrix, and whenever this matrix is given as the input, we will be getting the output as H. Okay, and in three-dimensional graphics, we have instead of a cube, what we require such a matrix 0, 0, 0, 0, and so on. This matrix will give you the output as a cube. And these are a few examples how we can have this two-dimensional graphics and three-dimensional graphics using matrices. Okay. Now, the basic transformations which we have learned in linear algebra, how it is being applied in computer. The basic transformations are scaling, translation, and rotation. Scaling, of course, you know, it is enlarging and compressing. How it is done? We can have the same picture of that sparrow or whatever bird. I'll call it sparrow for the time being. So we can have the picture of the sparrow. We can, this was the original image that we have shown here. This was the original image, but we can see that in this picture, it is slightly, the size of the sparrow is slightly reduced. And this is also a medium sized, and this is a bit enlarged one. Okay, so how this is being done? What is the mathematics behind it? So we have seen that this sparrow corresponds to a matrix. Okay, and in that matrix, we have the coordinates, say x, y, z, corresponding to the x-axis, y-axis, and z-axis, if you say. So we multiply those values with some scalars, so that if we multiply it with half, the size will get reduced. If we multiply it with 2, it will get enlarged by 2. If we multiply it with, say, 5, it will be enlarged by, say, 5 units, and we will be getting a very, very large picture. So that is what is called scaling. So what we have to do is we have to multiply with scalars C1, C2, and C3. So that is the concept of, so scalar multiplication is actually used for enlarging and compressing. That is what we have. S is equal to C1, 0, 0, C1, where C1, 0 corresponds to, okay. Is there any, hello, am I audible?
Okay, miss, no problem. Okay.
Because I had a message that my internet connection is unstable. That's why. No problem, right?
No problem. Okay.
Okay, shall I continue? Okay. Okay. Okay, fine. So the scaling transformation is given by the matrix C1, 0, 0, C2, because we know that 1, 0 corresponds to the vector along x-axis, and 0, 1 corresponds to the vector along y-axis. So C1 into 1, 0 plus C2 into 0, 1. That is what is given by the vector S, and that gives you C1, 0, 0, C2, and this is a scalar transformation in terms of a matrix. So if you multiply this S with some vector A is equal to, say, vector XY, what you will be getting is C1X, C2Y, and we will be getting the corresponding enlargement or corresponding compression. Okay. And in 3 dimension, we have 3 components X, Y, and Z. And so here what we have is, we have to multiply with the 3 coordinates, say C1, C2, and C3, and where each Ci's are the scalars. So exactly the same technique that we have used in 2 dimension, we will be extending it to 3 dimension, but with 3 components. Now the next method that we have is a translation. Translation means we will not be changing the coordinate axis we have, but we will be translating the object from one position to another position without anything happening to that object. That means without the alignment is not changed. Okay, that is what is called translation. I'll give you an example and you can see. See, if you see this, it is something like a chessboard we have, and this was the original axis that we had. And that axis are remaining the same, but this image is being shifted to slightly down. It is being shifted. And that the view of the translated image which we will be having is only this much. This portion will be black somewhere, and here on this corner you will have the picture. So we will be doing these techniques whenever we will play with Photoshop or we will play with images. We'll be doing such things, but what is behind happening behind this is the linear algebra of translation. Now, what is the mathematically how we will do the translation? We will multiply the vector xy1 in terms of 2 dimensions. I'm speaking xy1 is the corresponding vector. We will multiply it with the vector matrix 1, 0, x0, 0, 1, y0, 0, 0, 1, so that the final vector will be of the form x plus x0, y plus y0, and 1, where x plus x0 is the translation along x-axis, y plus y0 is the translation along y-axis, and 1 being fixed because it is a two-dimensional case. Okay, and in 3-dimension also we can have such types of translations, but it is a bit more higher matrix. That's why I have not shown it here. Now the next thing is what we have is a rotation. A rotation means it is a more complex transformation where we will be rotating the picture about the x-axis, y-axis and z-axis, and we can rotate the picture at any fixed angle. If you want, you can rotate it to 45 degree, or you can rotate it to 90 degree, or whatever angle you have, you can rotate it. And so these are some of the examples that we will be coming towards this. I just want to give you the rotation metrics. So the clockwise rotation and anti-clockwise, because we can rotate both directions. Clockwise rotation is possible, anti-clockwise is also possible. And so a clockwise rotation, this is the matrix that we have. We have to multiply this matrix with the vector corresponding to the image. And so this will give you r of minus theta. This value will give you the clockwise rotation, and counterclockwise rotation, this value will give you r of theta is equal to cos theta minus sin theta cos theta 0, 0, 1. This will give you the rotation about 90 rotation about 90 degree, or rotation about any angle that you want to have. So this is the example of clockwise rotation. This cat is being rotated clockwise 90 degree. This is the counterclockwise rotation. This cat is being rotated counterclockwise, and 180 degree rotation means this one. Okay. So rotation about x-axis, y-axis and z-axis, again you have the angles concerned, and so you will be taking cos theta, sin theta and so on here. So if it is a rotation with respect to x-axis, you have 1, 0, 0, x coordinates remaining the same, cos theta minus sin theta cos theta. Then the terms will move to the corresponding positions of x and y components. The y component, x and z component, and y component will remain to be 0, 1, 0. And that is the rotation matrix about x, y and z axis. So whenever you see such rotations taking place, you have to keep in mind that the matrix transformations that they're happening there is these types of matrix multiplications that are happening behind. Okay. Now we can have scaling, translating and rotating corresponding matrix multiplications we will use, and the transformation matrices and data matrix of the homogeneous coordinates we will be performing. Now the next important application of linear algebra is machine translation. Now what is machine translation means? Translation, the word meaning in mathematics means that we are translating one object to another place. But in a common language, translating from one language to another means we are converting from one language to another language. So in that sort of translation also, linear algebra comes into application. That is what is called machine translation. Suppose we want to convert a particular data which is available in French or in Chinese to English language, what you will do. So we will be discussing more about it in the further slides. But you have to understand that each word or each string of alphabets that we will say in computer language, we will be having those strings which corresponds to a string or a sequence of numbers. And those sequence of numbers will be assigned to a matrix, or they will be, if if in a particular sentence, one, if I'll be giving an example, say Ram is a lazy boy. So Ram, lazy boy, these strings will be assigned the value 1, and next sentence is there, Ram is a lazy boy, Sita is a beautiful girl. So we have Ram, lazy boy, Sita, beautiful girl. 6 words are there. Okay, so we will arrange these 6 words and we will assign values to these 6 words depending upon the 2 sentences. In the first sentence, Ram is a lazy boy includes only Ram, lazy and boy. So we will put 1 at the positions of Ram, lazy and boy. Okay, in the second sentence, we will be assigning Sita is a beautiful girl. So we will assign 1 to Sita, beautiful and girl. In the place of Ram, in the second sentence, we will put a 0. Okay, And correspondingly, we are planning, so that is what is called word embedding. Okay, that we have in the next slide. I'll slightly move on to that. Okay, I'll skip a few slides and come back to it, don't worry. Yeah, so that is what is called word embedding, and we have each sentence is being converted into, or each word in a sentence is being converted into corresponding ones and zeros depending upon the presence of that word in the sentence. Okay, and such things. So then we can understand that if you have in a computer, if you type some sentence, there is a mistake in that sentence, that word mistake is being easily understood because we have already a database which is having a lot of listed all these numbers and all this dictionary. The words in the dictionary, they are assigned numbers like 1, 0, 2 and so on. So depending upon these database, you can clearly understand whether in a language you have this word or not. Okay, and whenever you want to convert a word or a letter or convert a sentence from one language to another, what you will do is you will assign the words with the same meaning, the same letter. Okay, so if you have in English language, Ram is a lazy boy. In French, you have something corresponding to that, because I don't know French. I am not able to say that. We will be assigning some language there. Corresponding to Ram, there will be some name code. Corresponding to lazy, there will be a word. Corresponding to boy, there will be a word. And we will be having such a translatory machine. Okay, and depending upon these translations, we will be sorting the sentence, sorting the words which are having the same numbers, and we will be retrieving the data back. So that is what happens in the case of word embeddings and this machine translation that we have. Sorry, something is happening there. Okay, so I skipped a few slides. That's why I'm going back. Okay, so this is what is the source, and this is what is the language translation happens. Something like this. We have a source language here, we have a source language analyzer, and we have a source language dictionary, and each term or each word in that source language dictionary will be assigned a few numbers. Okay, and we will be having a sequence as we have done in the case of hashing and so on. So we have a source a language parser, and then a bilingual translator or bilingual dictionary. This is the portion where we have told that each term having synonymous meanings or having the same meanings will be given the same numbers, and we will be having a morphological generator and a sentence generator and the target language. So using that target language, the corresponding numbers will be replaced by the corresponding words, and finally we will be getting the target language. So that is happening in the case of translation, machine translation. And there are many techniques available for machine translation that you can read in internet or read in some literature. You can see there are a very numerous number of papers available in that. Now, linear algebra is the core of many non-data science algorithms also, and we can have a recommender systems. For example, if you want to purchase something in Amazon, how will you finally reach a particular product? You will surely deal with you will surely read the reviews and so on. Okay, so reviews, how many customers have purchased this article, how many reviews are there, how many have told that this is a good thing to be purchased, and such things we will be dealing with, and that is what is called recommender systems. And here also linear algebra comes into action. And we have recommender systems that are a class of machine learning that's happening, and recommender systems use the data collected. So here we have, that is why I told that this linear algebra has got a numerous application in data science algorithms also, because we have to analyze the data collected, we have to filter those data, and we have to take the which one is the best. We have to analyze the data very correctly. For that we use the linear algebraic techniques. Now, what are the linear algebraic techniques that you have, you want to have? Because we need the first thing we need is the characteristic information, that is the category or the price, the user preferences, location of the, and so on. Then the second type we have the user item interactions, such as ratings, number of purchases, and so on. And also we can see sometimes if you search the Amazon website, you can see that some pop-ups will be coming. The people who have searched for this item also purchased such and such items. Now, how the computer identifies it? Because it all happens in artificial intelligence, right? So how the computer knows that you are searching for such an item? Okay, so that is based on these type of recommender systems. Now, based on this, the developers choose one of the three commonly used algorithms, which are known as where we will use the hybrid systems, where we use the both types of information and recommendation systems and so on. Now, the filtering is done. How it is being done? Because the filtering is done by representing the information as a matrix, and then the linear algebraic techniques are used to filter out the unrelated information. And that is how it is being done. Okay. Now, the next interesting application of linear algebra is in computer vision, how we can see a picture in a computer. There also we use the linear algebraic techniques known as the convolution and so on. And the convolutional matrix is also usually known as the kernel matrix. And using this kernel matrix, what we can do is we can blur the image, or we can sharpen the image. Edge detection can be done. Other image processing functions also can be done. So as an example, I'll give you one example here. If this image, if this is the original image of the original matrix corresponding to the original image, it is a 6 by 6 matrix. And if you have a convolution matrix, something like 1 0 minus 1 1 0 minus 1 1 0 minus 1, it is a filter or convolution matrix. You have kernel, you will say. What you will do is you will multiply. It is not actually like our matrix multiplication. We will multiply 3 with 1 plus 1 into 0 plus 1 into minus 1 plus 1 into 1 plus 0 into 0 plus 7 into minus 1 plus 2 into 1 plus 3 into 0 plus 5 into minus 1. Such sort of multiplication is what is called convolution. You will learn convolution in Fourier also. That is using integration, but here it is using summation because it is a discrete thing. It is a finite one. It's not continuous, and so you will be taking summation here. So when you multiply, you can compute this 3 into 1 plus 1 into 0 plus 1 into minus 1. We will be getting, you can do it, 3 minus 1, you will be getting 2 plus 1 into 0 plus 0 into 0 plus 7 into minus 1, you will be getting minus 6 there. That's so total you will be getting 2 plus minus 6, that is equal to minus 4 plus 2 into 1 plus 3 into 0 plus 5 into minus 1, you will be getting a minus 3 there. And so that will correspond to the number minus 7 here. Now you have to move from left to right and from top to bottom whenever you're doing convolution. So moving from left to right, the next set of values that you have to choose is this is the 3 by 3 matrix that you have, that's shown in the dotted red line, and that will give you the next value, and correspondingly you will complete this. So one 3 by 3 matrix is here. So how many 3 by 3 matrices you will be getting? You will be getting 4 along this side and you will be getting 4 down. So output will be only a 4 by 4 matrix. So actually we can see that the image of 6 by 6 matrix is reduced to an output of 4 by 4. Okay. So the size of the matrix is reduced. Correspondingly, if the pixel size is reduced, the image becomes blur, or image becomes the clarity of the image becomes it's not of good quality. So for example, you can see that this was the original input image and we have done a convolution kernel of this and we got the output of this output as this image, which is a very blurred image. Okay. So that is the convolution method. Now word embeddings already we have seen, and there is one most useful word embedding technique is what is called the word to vec. Okay. Now again, the last application that I would like to discuss is the dimensionality reduction. So for example, if you are having a video recording for your class, you want to reduce the size of the video, or you want to reduce the image, because in some application forms and so on, you will be specified this, the resolution of the image should be this much pixels only. And so in order to reduce that size of the image, or in order to reduce the length of the video or the size of the video, what you will do is we will use the linear algebraic techniques again. And that is what is called dimensionality reduction. Okay, and the most famous approach to reduce the dimensions is a singular value decomposition, SVD, where essential parts to make our matrix computations simpler. We will be reducing a matrix. Okay, and these are the steps of topic modeling and so on. Again, somebody is interrupting. And these are the main references that I have taken for this class. And before I conclude, I would like to say a few more about the applications of linear algebra. You can see that there are many more applications of linear algebra, like eigenvalues, characteristic vectors, characteristic functions, and so on in the computer science. But as Rao sir had already told that it is mainly focusing on the 5th semester or 6th semester students of undergraduate level. What I have tried is, I have tried to introduce to them some of the applications that they will understand, and hopefully it is clear for the students. Thank you. Thank you for the patient listening.